Okay, I'm going to start out by talking a little bit about water flow. So, you have let's just say that this is your pipe.
Yeah.
And the reason that I want to start with water is because I want to show you the way, if you think about the way that water flows, when you're thinking about electricity, that it flows like water.
Yeah.
Okay?
Yeah.
Electrons instead of H2O.
2O, yeah.
Okay? So, you're going to have PSI. And that's pounds per square inch.
Yeah.
And that's the pressure that the water is coming into the pipe.
Yeah.
And we have directional flow. Now, let's talk about resistance. So, if we step down to a smaller pipe, now the PSI is going to be the same, but because you've added some resistance here, then your flow is going to be reduced. So,
Okay.
and that's going to be gallons per minute.
Okay.
So let's say if you reduce this by half, if you had 10 gallons per minute here, you would only have 5 gallons per minute here because you've reduced the pipe in half.
Yeah. Okay.
Okay. And then let's say that you have a valve, like a ball valve. And so you bring it down to there. So now you could shut it all the way off if you want to. You've got a valve here. So you can regulate this.
Yeah.
So it's a way to regulate resistance.
Okay.
So the more that you reduce this, the lower your flow is going to be.
Okay.
And what you'll find this to be important in in like installations of ice machines and that sort of thing, that you have a required amount of water for each machine.
Okay.
And so you have to test the gallons per minute to make sure that you're actually getting the required gallons per minute to that machine. So let's just say this is 1/2 inch inside diameter, right here, from here to here.
Yeah.
Okay. And then, whatever type of pipe that you have here, from here to here is going to be your outside diameter.
Okay.
So when you're dealing with water flow, inside diameter is the only thing that matters as far as the actual flow of water.
Okay.
So typically, all of the water supplies that we use for ice machines is going to be 3/8. It's going to be 3/8 inside diameter. And a lot of people use 3/8 copper.
Okay.
But if you use 3/8 copper, 3/8 is actually the measurement of the outside diameter, because that's how plumbers measure it, right?
Yeah.
Okay. But if it's 3/8 outside diameter, it's only 1/4 inch inside diameter.
Okay.
And that is very small.
Yeah.
You look at a 3/8 copper line and it's hooked up to an ice machine, and you say, oh, well, that looks adequate,
Yeah.
But yeah, it looks adequate to your eye. But as far as gallons per minute, you're trying to feed like a Hoshizaki ice machine takes a lot of water.
Yeah.
And you try to feed that with 1/4 inch inside diameter, you're not gonna get enough water to harvest the ice,
Yeah,
okay?
yeah.
So, we're looking at pressure and gallons per minute,
Yeah.
water flow, okay?
So would you go up on the copper to make it 3/8 inside?
Yeah, we don't use copper.
Okay.
We use fiber reinforced beverage tubing.
Okay.
You know, you ever seen it? Looks like that little white crosshatch string inside of it.
Yeah.
So that keeps it from, like, you know, popping holes. I mean, it's just a lot more secure. But it's 3/8 inside diameter, and
Inside down.
we use
Okay.
the same beverage tubing for any ice machine that we install.
Okay,
So
okay.
it really makes it easy.
Okay.
We have a lot of different ways to connect to different types of water supplies
Yeah.
and that sort of thing, but we use the same tubing no matter what. So water's easy to understand.
Yeah.
You know, electricity sometimes is not as easy. All right, but if you, it's kind of funny because if you think about it as the way that water flows, and water and electricity doesn't mix, you know.
Yeah, you're right.
But it's just as a concept. We'll have line 1 up here, and we'll put neutral over here. I mean, just for the sake of illustration on this one, because sometimes we use 208 volts, you know, 240. So in that case, you would have line 1 and line 2.
Yeah.
Okay. It still doesn't matter. Electricity.
It's still neutral.
Yeah, from the way that we're going to look at it, it's going to be flowing from line 1 to line 2, or it's going to be flowing from line 1 to neutral. Okay. Simple circuit. You've got wire that comes in, and we're going to have a switch. Okay. And then we're going to have a load. It could be any resistance, light bulb, motor, fan motor, compressor, it doesn't matter. That circuit is incomplete right now.
Yeah.
So you have to complete this circuit by bringing
The neutral.
a neutral to it.
Okay.
Or L2 if we were dealing with high voltage.
Okay.
And this switch, once you flip it, and it's like this, that's a complete circuit, and it'll energize that load. Okay. Now, do you know about contactors?
Contactors. Maybe.
Okay. Okay, so a contactor is like, it's a switch.
Yeah.
Right. And then you have a,
Normal open, normal close. Yeah, I
Yep.
got you.
you've got a coil. So this is usually like this. Boom. So if you put 24 volts on that coil right there, it's going to close that switch, those contacts right there, in order to transmit power wherever it wants to transmit. So you use this right here, and let's say that's the contacts, and then we're gonna need a transformer. So we'll pull it off of here, and a transformer has a coil, a big coil. I can come up to here. So as you can see, we've got 115 volts going to this transformer.
Yeah.
So then that is going to induce voltage into this smaller coil.
Yeah.
And that smaller coil is going to give us 24 volts. Okay? And what we're going to do with that 24 volts is we're going to go to the coil of the contactor. Now, we're probably going to want to put a switch in here so that that coil is not energized all the time.
Yeah.
Because what we want to do is we want to, when we flip a switch, it's going to energize this coil of this contactor, which is going to close this contact, and that's going to complete the circuit going to your load. And the purpose of using a contactor, we could just put a switch here, right?
Mm-hmm.
But the purpose of putting the switch down here instead is that when we flip this switch and energize this contactor coil, those contacts close rapidly. And when it's closing, the faster it closes, the less arcing you get on the contacts themselves.
Okay.
Okay? So that's why a lot of times we don't control things in high voltage applications with switches or anything like that. We like to do all the controls with low voltage, and then increase the speed of the contacts closing in high voltage.
Okay.
Okay?
Okay.
So that's basic electrical circuits. You know, one thing, you know, when we're looking at ice machines, we're going to have wiring diagrams that's got a lot of different components in there. And they're controlled in all the same ways. See, let's just say we're going to put in another load here. Those two loads are in series.
Yeah.
And we're going to put another load right here. What is that load?
I guess in series, all the three of them together?
These two are in series,
Oh, okay, okay, okay.
and this one
This one
is in parallel.
Parallel. Okay, I got you. Parallel.
Now that load is only in parallel with that load. Okay?
Okay.
So this load and this load are in series with this load.
Okay.
But these are in parallel. Not even really important to understand that very much. But you will see that one thing that every load is going to have in common is that it has to go to L2. So in you know, a lot of circuits, you'll see this. You'll see load, 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 load. They all go to neutral or L2 directly.
Yeah.
And then the other side of them has a switch, has a safety, an overload, you know,
Fuse.
a fuse.
Yeah.
There you go, right? And they'll all be controlled. They may go to the board over here. It's got power coming in here, and then it's got all kinds of different logic that's in here about when and where it wants to bring all of this on.
Yeah.
You know.
Yeah.
So, but whenever you're testing, usually you'll find a bundle wire of like a bundle of white wires together. You put one lead in there, and then you come over here and you start testing the other side of it with your other lead to say, okay, we got power there, power there, power there. We don't have power there. Oh, we're supposed to. Why don't we have power there when we're supposed to? So, yeah, that's how we do troubleshooting electrically. And we'll get into sequence of operations, but you know, if you know the sequence of operations of pretty much anything, like you can fix anything.
Yeah.
It's like
that way you can trace the problem back and see what's out of sync.
Yeah, if you know when it's supposed to be doing what.
Yeah.
If it's not doing it during the when, then you know you're looking at the problem. So like when we were talking about the way that water flows, the way that electricity flows in a circuit. The larger your wire, the more electrons can flow through it. Okay? If it's too small and you're pulling, you have more amperage, more electrons. So you've got voltage, which is also electromotive force. Okay, it's a type of pressure. You think of it as kind of electrical pressure. Okay, and so that's what is pushing your current, which is amps. Is your current.
That would, I get confused that the volts and the amps are different.
Yeah.
Yeah, that's when to use the volts and measure the amps and.
So, thinking in terms of water flow.
Yeah.
Why would you call it current?
Yeah.
If you look at a river, the water that's flowing down the river.
Yeah.
It's a current.
Yeah. So
right?
it's saying, okay.
So now you've got electrons that are flowing through the wire like a current.
Current, yeah.
Okay, so the more amps, the more current you have, the more volume of electricity, of electrons that you have that are flowing through the wire.
Yeah.
Okay, and what really becomes important in what we do, because electricity is a very, very complex subject, but it's not very complex for what we do. We only need to know what we need to know when it comes to it, right?
Yeah.
So one thing that becomes important is ohms, which is resistance. Okay. Remember we were talking about water and how when you reduced the pipe size, then it became resistance.
Yeah.
Okay. And the same thing would happen if we reduced the size of this wire right here. Like if you had a number 10 wire, 10 gauge wire, and you were pulling 30 amps through it, and then you reduce it down to 16 gauge wire. Now your resistance, we're going to reduce this down to a little wire right here. Now we're cramming all of these amps into this little bitty wire. And when there's resistance, those electrons, they're moving. Okay, so they're creating some heat energy. So the more resistance that you have, the more heat is generated. So when you increase your resistance right here, you're also going to increase your temperature. And if your temperature gets up to a certain amount, you're going to burn the insulation on the temperature. You're going to burn the whole wire up. You might burn
the transformers for like when you go down from 120 to like 24 volts. That was the transformer in there for?
Yeah, the transformer is really only there to reduce the voltage. And yeah, so you're using control circuit.
Control circuit, yeah.
You're using the transformer to reduce the voltage and the amperage and everything in there, reduce the heat. You can use smaller wires. You know, you can use smaller components.
Yeah.
So like, you know, we typically talk about 115 to 24 volts, right? But you'll see in our ice machines, sometimes we use 24 volts, but there's usually a little transformer, especially in the Hoshizakis, that bring it down to 10.5 volts.
Okay.
And it's still AC, 10.5 volt AC. And the reason that you step it down to 10.5 volts is so that the board can pass power according to its logic. Because if you look on the board, you'll see there's these little relays that's on the board. They're tiny little relays. But because, you know, you stepped it down to 10 volts, then it can pass power easily, you know, out to other relays that are low voltage that can close contacts to pass high voltage. Okay. So, you know, you wouldn't purposefully reduce the wire size like this. Okay. But you'll see it in the field. Where somebody went and put a smaller gauge wire on, because ice machines don't come with a cord. Okay, so you have to actually put the cord in the plug-in that you want on the ice machine. So you'll see people use smaller gauge wire than it's rated for. Now, you won't see that from our guys. Right, because we don't do that. Oasis doesn't do that, but you'll see it where some people have done that, and they'll use even a plug-in that isn't rated. If you have a plug-in that's rated for 15 amps that you put on there, this machine's rated for 20 amps. Well, now you've got kind of a pinch point. You've created a point of resistance. So that's why it's not rated to flow that many electrons. All of a sudden, a lot of electrons are being pushed into a small point. Temperature goes up, burn up the plug-in, burn out the outlet, you know, and everything like that. So we use resistance to troubleshoot with a lot. Because you've got a float switch. So when it starts out in the fill cycle, so the water valve energizes, the sump starts filling up with water. Okay, and there's a float that is coming up as that sump's filling up. Well, when the sump's full, the float tells the board, okay, the sump's full. So boom, it shuts the water valve off. Okay. Well, then it goes into a freeze cycle, and as it's pumping that water up over the evaporator, that water is turning into ice, and so the water level in the sump is going down because it's turning into ice up on the evaporator, right? And it's being circulated over. Okay. Anything that's not ice goes back into the sump. It turns into ice, then that water level drops.
So it will fill up, and then the pump take it and run it over the evaporator, it freezes. As it freezes, it goes down.
Exactly.
Okay. Yeah.
And there's different ways for different brands of ice machines to decide that it's made enough ice already and it needs to harvest the ice.
Yeah.
But you know, I'm specifically speaking about the reason how we use resistance to troubleshoot.
Mm-hmm.
Okay, so we're just talking about a Hoshizaki machine. So that water bath in the sump, once it goes down to a certain level, the float knows what's level high, it knows level low. So when that float gets all the way down to the bottom, it tells the board, we're out of water in the sump. We've made all the ice that we wanted to make, so the board, you know, puts it in the harvest. Okay, well, if it doesn't go into harvest because that float's bad, okay, so it didn't tell it, so it's going to continue making ice. Yeah. It's going to that whole evaporator, and then there's going to be no water to make ice with, and it's going to stay in ice, and it's just not going to go into a harvest until it reaches, you know, 50 minutes or something like that, and then it would go into a 3 beat. All right. Oh, there you go. There's a float switch. Like this. See that? Yeah. So that's water level low. And then that's water level high. Yeah. Okay. All right. So if it doesn't harvest, then the board's going to say, hey, 50 minutes still hasn't gone into a harvest, knows something's wrong, so it's going to shut off, and it's going to start beeping 3 times. Okay. That's to protect the machine. Okay. It would freeze completely and totally up. You can get evaporator separations. I mean, it could really damage the machine. Yeah. And the opposite of that is that it goes into a fill cycle, right? So this is coming up as it's filling. It gets all the way to the top. And this is bad. Okay, this float came up here, but electrically, at the end right here,
it's not sending the signal.
It's not sending the signal to the board.
Yeah. So
it's going to continue to fill. Okay. Now it's never going to go off on a beep code because that can't damage the machine. Okay. All right. It's got a standpipe in there, so it just overflows. Oh. Okay. It just keeps overflowing. It's filling, overflow, and then it checks the float switch. It fills. It checks the float switch. Fills. Checks the float switch. Okay. So, so you walk up to a machine, and you hear it filling. The water's just. Then you hear water going down the drain, and it's constantly water valve energizing, water going down the drain, and it's just sitting there doing that. Yeah. And 5 minutes, 10 minutes, right? You walk up to it. Yeah, it's been doing it ever since this float failed, and then the customer called and said, "Hey, our ice machine's not working." Yeah. Okay, so maybe that day, maybe next day, we show up there, still doing the same thing it was doing when it stopped making ice. Okay, and so in that situation, experience will tell you probably, oh, float switch, just go ahead and change it out, right? I mean, because you've seen this a bunch of times. But we use resistance to test this float switch right here, because when it's full of water, okay, you pull this off right here. You look in there and you see that sump, it's full of water. You just cut the machine off, right? This one goes up to the board. There's 2 wires right here, a black and a red. And then it's got, if you can see, right here, those 2 metal tabs right there. So you just put one lead on one of those metal pads right there, and then you put the other lead on the other metal pad with your multimeter in ohms, because we want to test
the resistance.
And what we want to have is continuity. And what continuity is let's see, it is less than 1 ohm. Okay.
Less than 1 ohm.
Because ohms is a measurement of electrical resistance. And continuity just means that there's a free flow of electricity.
Yeah.
There's nothing holding it back, really.
Yeah.
You know, so for the board, that gives us a really good signal. And we use continuity for bin control as well. Okay. So once the bin is completely and totally full of ice, it needs a way to be able to tell the board that it's full of ice.
Yeah.
Okay. So we have a couple different styles. There's thermostatic, there's mechanical. Okay, so let's just take a mechanical bin control. It has a flap.
Yeah.
Okay, and basically the flap is just a switch.
Yeah.
So once that flap is closed, now from this point to this point, you have continuity.
Yeah.
Less than an ohm.
Yeah.
So if you walk up to a machine and you can see the ice is up over the bin control, you know, that bin control is buried in there. So obviously it's not communicating with the board and telling it that the bin control, that the bin is full of ice. Okay, well, another one of those things. It's obvious, right? Bad bin control. But if you wanted to test that bin control with that flap pulled in, you want less than an ohm. Okay? Now, why would you test a bin control? Sometimes it's not obvious. Sometimes you get there and it is actually off on a full bin. Okay? But you know, you've had a freeze up. And you want to know why did it freeze up, you know, and you get there, and at the time, well, there's no ice in there because all of the ice is melted, you know, or they've used it or whatever, so it's not down in there. And so now you're going to do a freeze up checklist. You're going to check everything. You know, you're going to ohm out that bin control.
Yeah.
If you get 1.2 ohms, what do you do with that bin control?
Throw it away.
Because it's not what?
Yeah, less than
It's not less than an ohm.
Yeah.
Okay, or at least 1 ohm or less. I would probably still
replace it. I mean.
at an ohm. Yeah, but we want less than an ohm.
Yeah.
Okay, because I mean typically, you know, what I've seen when you ohm them out, it might be 0.3, 0.4, 0.5, something like that. When you get up around an ohm or higher, it could cause intermittent problems. You're just not really getting that signal to the board that the board can read. It can't understand it if it's not less than an ohm. Okay, so so that's how we use resistance, ohms, to troubleshoot with a lot.
Yeah.
Okay, but sometimes we also use voltage. So let's put a simple circuit here with a load. Okay, we're going to L1 and we're going to neutral. All right, you put a lead here, and then this is a 115 volt circuit. Okay, all right, so then you put a lead here, and you've got 0 volts, nothing, and you're like, well, what could that possibly be? So then you put your lead here. 115 volts.
It's the switch.
Exactly. Okay.
It's open.
And you can verify by coming over here. And you still got 115 volts. Because if this was actually closed, from there to there, would be 0.
Yeah.
Okay? Because it's like the same line, you know? So, we also use volts to troubleshoot with in a lot of occasions. Where do we have power? Where do we not have power? Where should we have power? You know?
See where it stops flowing and trace it back. Check your switches.
I just have one more thing on transformers. Like we said, we've got 115 to 24 volt transformer, most common transformer in the history of mankind. Okay. You'll see this one in some flakers. Alright, we've got 115 volts here. From here to here, we've got 24 volts. Now, where do we get 10.5 volts from?
We get 10.5 volts.
Let me show you. That's 10.5 from here and there. This is what you call a tap.
A tap.
Okay. Anywhere in that coil, you could put a tap and get anywhere between 0 to 24 volts.
Okay.
Now, we don't put those taps in there.
No.
All right, this is just, instead, this is a transformer. It's gonna come like a box. It's gonna have 2 wires in for 115 volt. It's gonna have 1 wire out. It's gonna have 3 wires out. From here to here is gonna be 24. From here to here is gonna be 10.
Okay.
And it's probably gonna even have a connector on it. So
Yeah.
all you do is just plug it in to the board or whatever, you know. But but just terminology matters.
Yeah.
Because this 115 volts coming in, this is going to be your primary voltage.
Yeah.
Okay. This 24 volt is going to be your secondary. That's probably all you need to know, but just for the heck of it, that 10.5 volts.
Yeah, they helped me out there. I never known that.
That 10.5 volts right there, that is going to be tertiary.
Yeah.
Okay. But so, you know, when you're troubleshooting with somebody on the phone, it's like, hey, you know, what are you getting on your primary side of your transformer? You know.
Yeah.
So you're going to want that 115 volts.
Yeah.
It's like, okay, all right. Well, now what are you getting on your secondary voltage? You know, what do you got going to the board? This 10.5 volts, we know that it's there specifically to power the board.
Yeah.
So, you know, when you're looking at a wiring diagram, you're going to see that coming from that transformer is going to be leading directly into the circuit board somewhere, and you're going to want to check voltage there. Is that board getting power to the board? There's no lights on it. You know, it's like, why? Is it getting power? Why is it not getting power? You know, is it a fuse blown, or you know, or is the transformer blown? You know, hey, we're getting power coming into the transformer.
None coming out.
We're getting nothing coming out.
Yeah.
We've got a bad transformer.
Yeah.
So we use volts and ohms to troubleshoot with. Guess what? We use amps to troubleshoot too.
Okay.
All right, because we have a load. Simple circuit again to a load. L1 in neutral. Okay? So this load, let's just say it's a resistive load. Okay? As opposed to a motor, which is an inductive load, which honestly for our purposes doesn't matter. We just need to know how many amps is this load supposed to be pulling.
Yeah.
Okay, let's say it should be pulling 10 amps, and we use and we're going to go over like meter use a little bit. We'll go out in the warehouse and actually go over, you know, just the how to use the meter and what you put it on for amps, volts, ohms, capacitance.
Yeah.
Okay, but for our purpose, this load should be drawing 10 amps, and the reason that it's drawing 10 amps, it's 115 volts. Okay.
Okay.
And the resistance in this load, let's just say, you know, like I said, it's a resistive load, like a light bulb or something like that. So that resistance, the higher that resistance in a resistive load, the lower the amps.
Okay.
Because the amps can't get through that resistance. Okay, it's slowing it down.
Yeah.
All right. Because if you didn't have a load here, your amp would basically be whatever your breaker was.
Yeah.
All right, you
Yeah.
trip the breaker. All right,
Yeah.
so you have that load in there, you know, slows it down.
Yeah.
So it's supposed to be 10 amps,
Okay.
and it's gonna be causing some heat. You know, you see just like an incandescent light bulb.
Yeah.
You know, you see it's warm to the touch. It's a resistive load. It's creating light, but it's also rejecting heat. Okay, and so we use a clamp meter on our multimeter. It clamps over the wire. Okay, so you put it on amps, then you put that clamp over the wire, and then it's going to tell you how many amps is going through the system.
Okay.
Well, let's say it's only 2 amps.
That's not enough for the load.
Yeah, there's a problem there.
Yeah.
You know, that's supposed to be drawing more power than that. That's telling me that, you know, there's more resistance in that circuit somewhere than there should be. Okay. Not very common. Usually, if you're not pulling the full 10 amps, you're probably pulling 0 amps.
0 amp.
Okay.
Yeah.
So if you put your clamp over there and it's 0, well, something's probably not getting power. So now we're going to go back to using ohms and volts to try to figure out, you know, why it's not getting power. But if we come and check it and it's 15 amps, and you know it's supposed to be 10, you've got the manual, you look in the book right there, it's running load amperage is 10 amps, and you're pulling 15 amps, now you know you have another problem. Okay, so yeah, we use it all.
Yeah.
You know, just whatever is. Sometimes you use all 3. You use whatever you have to be able to solve these problems. And I think let's take a break. I think that's
Okay.
we can pause there for our electrical.